Okay, so welcome everybody to WAFERS 2021, the second workshop on validation and verification in future cyber-physical systems. My name is Leonardo Montecchi from the University of Campinas in Brazil, and I am co-organizing this workshop and workshop chaired together with Nuno Laranjeiro from the University of Coimbra, Portugal, and Vince Molnar from Budapest University of Technology and Economics in Hungary. Unfortunately, we are not in Florianopolis. We have to do this workshop remote, so we are not able to see these palms and this beautiful scenario. Maybe we hope for the next edition. What is the objective of this workshop? So it is to discuss novel dependability assessment approaches for cyber-physical systems. So the focus, as also the title of the workshop, is cyber-physical systems, with the objective to see new techniques, both from academic and industrial perspective. It is the second edition, so we had the first edition of WAFERS at LADC 2019, and this is the second also at LADC. It is a workshop which is emanating from the ADVANCE project, which is a European project which involves partners from Europe and Brazil and Colombia, Europe and South America, on these topics. And we had three kinds of contributions. So we had regular papers, short papers, and also we allowed emerging ideas, so very short papers. This resulted in 8 papers that have been accepted to the workshop. So this is the program taken from the LADC website. So we have a first session now with four papers chaired by Tommaso. Then we will have a break and the keynote from LADC Sbesk. And then a second session chaired by Edson Tavares de Camargo in the afternoon with more 4 papers. And we will have, so videos will be played of these papers, and then the authors will be here to answer questions and discuss. So that's it. Thank you for coming, and I think we can start with the session.
Thanks, Leonardo, for the introduction. So nice to meet you all, everybody. So even if it's afternoon, evening, night, somewhere in the world, wherever in the world you are, thanks for joining this session. I am Tommaso Zoppi from University of Florence, and I'm here to coordinate this session, which has a very heavy Hungarian imprinting, because there are many papers which are coming from researchers working in that country. And I think this is overall good for the conference, so that essentially we are exchanging works that are done towards 2 different sides of the Atlantic Ocean. So something from Latin America and something from Europe, Eastern Europe. Okay, so let's start for the first paper. First paper is entitled Towards the Formal Semantics of Scenario Tests for Autonomous Vehicles. And the presenter here is Laszlo Kovács, which is a freshly graduated MC, computer scientist, and field of specialty is model-driven software development, and his main field of interest inside this broader model-driven development is domain-specific languages, graph transformations, and design space exploration. Aside from being graduated, he also worked for Ericsson for 3 years, and now he's collaborating with the Budapest University of Technology and Economics. So please, Laszlo, floor is yours, and I think we can play the video also.
Hi, my name is Laszlo Kovács, and I'm the author and the presenter of this paper. and the co-author is Dr. Oskar Semmerat, and the paper's title is Towards the Formal Semantics of Scenario Tests for Autonomous Vehicles. The motivation behind the paper is that almost 8 billion kilometers are necessary to make a statistically significant comparison at confidence of 95% to show the failure rate of an autonomous vehicle is lower than the human driver failure rate. This takes a lot of resources to do so, like money, time, and equipment. Also, if the specification of a hardware or the program's structure has been changed, all this testing has to be started over. Possible solution to get around this problem would be to create a tool that is capable to test autonomous vehicles by simulation. To do so, we need to generate every kind of traffic situations what can occur in real life. So we propose a tool or a testing framework, what is a work in progress concept, to be able to simulate real life situations in simulators. First, we generate the map, the environment, where the traffic situations will take place. To do so, we can import existing test tracks, transfer them to increase the diversity, or simply synthesize them from different sources, for example, from Google Maps. With that, we get the map file. After that, we generate the abstract situation, what describes the sequence of events in a very general way. With that, we have the actors, which are included in the situation, and the situation itself. Just like in real life, the actors have different kinds of behaviors, and they decide how to behave depending on the actual situation. In the simulated environment, we have to generate these behaviors and the possible sequences of them, and assign them to the actors. Then, we generate different layouts based on the situation and the actors, and apply metamorphic scene mutation on that to get rid of the test oracle problem and get a more diverse result. With that and the behavior we get seen, what can be handed over to the simulation for execution. One use case of the simulator is to get a physically proved feedback if the assigned behaviors are correct or not in all the layouts. On the other hand, we can supplement the simulator with an already trained AI, what is used in the already existing autonomous solutions, and let it do its job, recognize objects, and make decisions based on them and the actual parameters of the vehicle. With that, we can monitor whether it decides the same as the expected behavior or makes incorrect decisions, and if so, why. In this slide, we see a state flowchart that describes the sequence and relations of behaviors in a concrete situation. With that, we can capture the abstract dynamic of the situation. In the left-hand side, we see a picture about the abstract situation that describes the environment and where the actors are placed on it. And in the last picture, we see example outputs from the simulator, where the two previously presented concepts have been put together. In that picture, we can also see the AI work, as the identified objects are surrounded with black rectangles. There are some prerequisites of the simulation. To be able to simulate, we need a corresponding model, both for the environment and for the behavior of the actors. Every action of the actors results in model state change, thus we need model transformation rules. A suitable tool is necessary, but actuate these graph transformations. These pictures shows the metamodel for both the scene and the behaviors. The scene has two different kinds of components. The logical difference between these two is that while static ones can change their position, dynamic components can. Dynamic components are the cars and pedestrians, while the static components are the different parts of the environment, for example, roads and lane segments, what are the smaller parts of the road. Every dynamic component has a behavior list, what holds the behavior sequence of the given actor. Every behavior list are assigned to a specific scenario, thus the scenario is aware of what behavior is active and what shall come. This is important if we want to compare the predefined behaviors with the decisions of the AI. The scope of this paper is to provide well-formalized graph transformation rules, propose a tool and a possible way of solution to enable simulation to show the relevance of the idea, and provide a tool to prove the usability of the proposed transformation rules. This tool implements the transformations and also capable to explore the reachable states from a traffic situation instance model with applying them. The proposed tool uses Scala Simulator, what uses a tool called Scenic to define scenes and with that enables to specify behaviors for the actors. Scenic has 5 predefined behaviors, but 2 has the purpose to follow specific trajectories, what are not relevant in our case, thus I only implemented the walk forward, follow lane and lane change behaviors. Although these are not able to capture the full set of possible behaviors, what a vehicle is capable of. For example, they don't let the vehicle off the road, but in a dangerous situation, a vehicle can decide to leave the road to prevent an accident. For another considerations, I implemented a dedicated behavior for crashing, because in some cases we want to simulate a situation where a crash happens to see the result and the impact of it based on different trajectories leading to that accident. The figure in the bottom of the page shows an illustration about the logically reachable states. The expected states are the ones what are reachable with the Scenic behaviors. The possible states includes all the states reachable in the simulator, and the invalid states are the ones what breaks the rules of physics. So, how these graph transformations work? The predefined transformation rule is the left-hand side precondition, and we look for a match in the actual model, as you can see in this animation. If we have a match, we rewrite the existing model to get a new graph. Everything what is present in the right-hand side and in the left-hand side too stays the same. What is present in the left-hand side but not in the right-hand side gets deleted, and what is present in the right-hand side but not in the left-hand side, it gets created. As I mentioned before, we want to execute these transformations multiple times in different orders to reach a model state what is relevant in the specified situation. This can be, for example, a model state where a dangerous situation is present. To do so, we use a method called design space exploration. We have the initial state of the scene model, and with an algorithm, we apply the possible graph transformation rules in all the possible combinations. If the model reaches a state what is invalid in the context of simulation or breaks the predefined conditions, the application drops these states and steps back to a state what is not invalid and applies different rules if there's any. A predefined condition can be a state where the examined vehicle already left the critical place in the situation, therefore there is no chance for the dangerous situation to form. The created tool's output is a segment of a Scenic file what captures the different actors' behavior patterns. There are some static Scenic keywords which also came from the behavior model. The tool executes the design space exploration, and if the scene model reaches a valid state, then it generates the Scenic code from the found trajectory what led to the model state. We used Eclipse modeling framework as a modeling framework, Viatra for the model queries and transformation rules, and Extend to connect the Viatra rules with the executable Java environment. To sum up, we created well-formalized graph transformation rules to capture the possible behaviors of the autonomous vehicles to enable the simulation of them. We created a tool to execute design space exploration and model transformations what realizes the aforementioned behaviors. Work in progress developments are to connect this tool with the simulator, to give a confidence metric for test suits, and to extend the set of rules to increase the range of usability of the tool. We are also working on the automatization of parsing the output to get the complete Scenic file with one process, and to optimize the design space exploration to decrease the execution time of the tool. Thank you very much for your attention, and please ask your questions if you have any.
Well, thanks a lot for the video presentation. So I believe that the presenter is here. So presenter, if you want to show up on the webcam, just to look at the attendance and to ask for questions personally instead of just being hidden somewhere. Otherwise, I will do this. So first, we are asking to everybody here if they have questions about this very interesting presentation. So don't be shy. Feel free also to write on the chat if you want.
Yeah, I'm here. Hi, everyone.
Okay, perfect.
I'm
so you see the presenter is here.
I'm struggling to share my webcam feed.
No, I mean, I was just joking. Don't feel forced. Okay, so in the meanwhile, I will start with some questions. Question is, you talked about some design space exploration. Do you have any problem in very huge complexity or very huge time needed to really explore all the states or all the state space? I mean, this state space, I believe it can be very, very huge depending on the model that you have. So do you have any way to cut down a bit the complexity of this? Are you using some optimizations?
We are aware of the thing called design space exploration. Well, not the design space exploration, the explosion, I would say. And as my thesis, I implemented a similar application what used the design space exploration, and I modified the exploration algorithm to reduce the available graph transformation rules in every step, and with that we get a more narrowed down trajectory. What can be applied, what can be can come out as a result throughout the exploration, and with that we significantly reduce this thing to happen. So we made some modification to fasten up the process.
Okay, thanks for the answer. Any other question, curiosity from somebody else?
Yes, I have a question also. I've seen that you have used a simulator, no? You were mentioning about Carla, and I was curious to know how is this connection with the simulator done? So if you do some analysis of the logs, or how do you get the information from the simulator?
I mentioned to Carla in my presentation, but just for the sake of the big picture, that's not my part, how I do this. So my responsibility is just to provide these trajectories, to provide the scenic file. After that, how these handled and how this fed into the simulator is beyond me, and the other guys work on that, and I'm pretty sure they will, the following presentations or presenters will be able to give relevant answer for that.
Okay, I understand it. Makes sense. So it was not part of this work exactly. I mean, it's complementary to what you are doing here. Yes, I understand. Okay.
Yeah, I felt important to provide a big picture why this is relevant and how this will be applied. Yeah.
Sure. Okay, thank you.
Okay, then at this point I'm curious. This pipeline of development from the simulator to different tools, is this something that is developed by different people inside the university, or is something that you carry out together with some other partners, industries, or whatever? If you know it, I mean, it's
It's from start to the end. It's all developed in the Berkhoff University, so it's not an outsider thing. Basically some of the upcoming presenters will be also involved in this production or development. So it's a university thing.
Okay. So thanks again to the speaker. And I believe we can move to the second presentation.
Tommaso, just a moment. Let me do an announcement. So I see that some people here in the list of users, some of you have just the symbol of headphones and not the microphone. So this means that the system is not using the microphone. So if you want to talk, you need to refresh or enter again in the system and choose in the beginning to use the microphone. And then you should have this a symbol like this with a microphone, red microphone or green microphone disabled, which means that you can talk. Okay.
Maybe in the meantime, I found out what was wrong. So
But yeah, just because I see that there are some people still maybe this may not be clear for everyone in the beginning. So okay.
Okay,
please
so
go
I
on, Tommaso.
thank again the speaker, since now we are also seeing him, so we can thank face to face. And so we are moving to the second presentation. I also remember that you can also type in the chat, even if your mic is not working. Okay, so we are also reading questions there. So second speaker is presenting a work which is entitled Towards Testing the UML PSSM Test Suite. And this paper is going to be presented by Marton Alex, which is a PhD student at the University of Budapest, University of Technology and Economics. His research interests include software testing and graph databases, and he is a contributor of the LDBC social network benchmark. Also, he participated in the Arrowhead Tools and Embrace EU projects. So for sure, he is more than just a PhD student, because he already worked in many, many projects. Okay, so I see that the presenter is here, and I believe we can play the video as well.
Welcome everyone. My name is Márton Elekes. In the following, I will introduce you our paper about evaluating the precise semantics of UML state machine specification. In model-based engineering approaches, models play a central role as the base of information exchange and analysis. Models can be executable and used for simulation, code generation, and verification purposes. Precise semantics for these models is crucial. If we want to have model editors, they should behave the same way. For example, they should do the same syntactic validation of models. If we want to do code generation, the generated code should have the same behavior. And also in case of testing, simulation, and model checking, we must know the semantics precisely. UML is a general-purpose modeling language for software systems. It defines several types of diagrams for visualizing different aspects of systems. To relieve the lack of a precise semantic definition, the Object Management Group created the foundational subset for executable UML models, FUML, and the precise semantics of UML state machine specifications. PSSM consists of two parts: a textual specification of the execution semantics, and the test suite to validate that model execution tools conform to the specification and also to illustrate the semantics. Our goal was to evaluate the PSSM test suite. Is there any errors in it? Is it suitable to assess the correctness of tools? How does it help understand the specification? We collected recommendations in order to enhance future modeling language specifications to be more precise, comprehensible, easy to use, and also to have fully conformant tools by making testing more rigorous. The PSSM test suite consists of 103 test cases grouped into 18 categories. The tests were manually created by experts based on more than 100 requirements extracted from the normative text of the UML specification. The tests specify the diagram of the target state machine, the stimulation events the tester sends to the target, the expected execution trace the target should produce, and any alternatives, if exist, an explanation about the test and its purpose, and the detailed run-to-completion steps. The specification also contains the test suite in an executable format in XML. Let's see an example test case from the transitions category. The test defines the target state machine on the right, the inputs it receives, the expected trace produced during execution, and the detailed run to completion steps with the event pool, the active state configuration, and the fired transitions. It states the purpose of this test, which is to demonstrate that completion event occurrences have priority over other event occurrences already in the pool. The execution starts with the initial RTC step when transition T1 is traversed. In step 2, the state machine is in state wait. All behavior of that state is executed, since there is none of them, no entry actions, no do activity. Therefore, the state generates a completion event, and the tester sends a start signal. Since completion events have priority, it is dispatched first. There is no transition triggered by it from the active state, so the event gets lost. And the next step is step 3. Here, start event is triggering T2, and S1 is the next state. S1 has an entry action which is executed and prints out S1 entry to the trace, as expected. After its behavior complete, state S1 generates a completion event, and the tester sends a continuous signal. Since the completion event has priority, it is dispatched and triggers T4, which is a completion transition marked with the lack of a triggering event. The effect of T4 is executed, which prints to the log. State AND is entered and generates a completion event. The completion event still has priority, therefore the completion transition T5 is traversed and the test ends. So this was a simple test case. We found no prior work on evaluating the PSSM test suite. Therefore, we started with common verification and validation techniques. We reviewed the text of the specification along standard review criteria, for example, consistency, unambiguity, completeness, and so on. We reported the errors found to OMG. We also executed the test suite available as an XML document in a UML execution tool. During the review, the typical bugs we found are the following. Due to the manual specification of the tests, there are more than a dozen inconsistencies in them. For example, the event pool in this RTC step refers to a non-existing state. Others refer to existing but wrong states or transitions, which can be misleading. The RTC steps, the tools realize, are not verified. Therefore, mistakes here cannot be revealed by a test execution, only by a review. The exact timing of input signals is problematical. The text suggests the active state of the target when the signal is sent is specified. However, the tester implementation does not check the active state, which is reasonable since it has no way to inspect the target state machine. The traces only record the output signals the target sends. The order in which the input signals are received and overlap the output signals is missing. This is a problem because the test cannot verify that each output is sent after the input was received. The parallel execution of orthogonal regions is a hard-to-understand part of the UML. Although a few test cases verify this, corner cases where effects or even their internal actions overlap each other should be illustrated with test cases. PSSM permits multiple execution orders in certain cases, for example in orthogonal regions. Therefore, alternative execution traces can also be valid. In most of the cases, these alternative traces are listed in the specification. However, in some tests, certain execution traces are missing. This would cause correct execution tools to be declared non-conformant, and valid traces are not considered during model design and in verification tools. Another controversial part of the specification is the atomicity of do activities. For example, this state machine can be executed by traversing T1.1, then executing the entry action, starting and completing the do activity. After that, a data signal is received, the exit action is executed, and T1.2 is traversed. In an alternative case, after the entry, the do activity is started, but a data signal is received and aborts the do activity before it can print to the execution trace. So do activity is only partially executed, then exit action and T1.2 follows. In the test suite, there are contradicting examples where this abort can happen anytime or only while waiting for signals. The list of alternative traces can be huge, in some cases longer than a page. It is hard to understand or find the small differences in a list like this. We executed the test cases in Camel Systems Modeler, a model-based engineering tool which is stated to support PSSM. The advantages were that the test suite implemented in XMI is part of the specification, and the tester sends input and the test verifies the execution traces automatically. In the Camel simulation, it is easy to follow the execution, the active and the visited states of transitions. One of the difficulties is that importing the XMI file and resolving the dependencies is complicated. Since the import displayed several warnings, we refrain from evaluating the conformance of the tool with full certainty. Because of this, we had to send the stimulation events and verify the trace manually. Another common difficulty in the simulation tools is that we cannot choose from alternative executions. We found that a few advanced elements are not supported, and some complicated or not recommended elements are wrongly executed. We collected a few recommendations to enhance both PSSM and future modeling language specifications. It is beneficial to generate parts of the test cases. For example, the expected trace can be generated by a reference implementation. The difficulty is that the simulator usually generates a single trace only, or more, but in a non-deterministic way. We suggest a more rigorous check of traces, including the order of both input and output signals. If the test builds on the active state of the target state machine, a way to monitor it should be defined. The alternative traces should use another representation, for example a graph, instead of a long list. Official guidelines to help the import of the XMI format to the tools would be beneficial. We think that the reference implementation and the test suite to assess the correctness of other tools is beneficial on the prevalence and interoperability of the language and these tools. We believe that aiming for tooling and semantics in the early phases of the specification development can help to find flaws and inconsistencies. To conclude, we argued that precise semantics for modeling language specifications is required in order to have correct editors, simulators, or verification tools. The PSSM test suite is a huge step forward, and it helps to understand the specification and assess execution tools. We reviewed and executed the test suite and found inconsistencies, missing traces, and ambiguous elements. We collected recommendations like using a systematic approach and adapting test design techniques for verification of modeling language semantics, and using tools to generate parts of the test suite. In the future, we plan to partially automate the generation and validation of modeling language test suites using formal verification methods. Thank you for your attention and feel free to ask questions.
Thanks for the video presentation. Okay, so we have the speaker here, which I believe is happy to take questions. So please feel free to take over the mic and ask all the questions you have.
Yeah, I have a question. It's more curiosity. So you said that you found these inconsistencies and problems in the test suite. I've got two questions. So the first is this test suite is, is this test suite final, or is it still being developed by the OMG? And
I hope it is under development, but it's a 1.0 version, so I think it should be in a stable state.
Okay, so it's supposed to be in a stable state. And if what are you planning? What your team is planning to do? If you are planning to send recommendations and something, I mean, or if you have already sent and got some feedback from the OMG, or I mean,
we've already issued at their issue tracker about these inconsistencies, and the deeper things they found, that should be a bigger task, because redesigning or rethinking some major concepts like what is the atomicity of certain actions is a bigger thing than just opening an issue. So we will dive into that topic more deeply. That's the plan.
Yeah, understand. Well, it's very interesting. Yeah, congratulations.
Thank you.
Okay, I have another curiosity, which is connected to what you said in the future works, because you mentioned that you are planning to automatize something in the test generation phase.
Yes.
I saw that you needed domain experts to generate your 100-something test cases. So what you think it's easier, it's more immediate to automatize out of all this process?
I think that they had a reference implementation at their hand when they designed this OMG task group designed the PSSM. So, for example, the main trajectory, the main execution trace they recorded or specified in the test, in the text of the specification, it should have been done using that reference implementation, and that implementation should have logged its steps, and that would be one execution trace, and it could be used to specify that this is the expected one. Since they only had a simulator that can be used to generate all the other execution traces. So that's a bigger task, because a model checker is needed to generate all the possible traces, and we already saw that that they missed some traces. So that's not easy to list all of them manually. That's the easily generatable parts. Other parts of the tests, that's the stuff. I think that, for example, combinatorial testing to check that more combinations of modeling elements are checked in the test suite can be used. Or yes, that would be my first guess to move forward.
Okay, thanks for the answer. I think we have other 1-2 spare minutes of time for questions, if there is some people in the audience who wants to ask. Okay, otherwise we thank again the speaker for another brilliant presentation. So thanks, Marco. And we are moving to the third presentation of this session. Title of the paper is Impact Assessment of IT Security Breaches in Cyber-Physical Systems. And this paper is presented by Andras Foldvari, who is a PhD student at Budapest University of Technology and Economics, as his colleagues. His research topic is quantitative modeling for dependability, facilitating expert engineering interpretation and verification, validation of results. So please, I see that the presenter is here, and I believe that we can also play the video.
Welcome everyone, I'm András Földvári, and I would like to present you our research, Impact Assessment of IT Security Breaches in Cyber Physical Systems. With the increasing availability and usage of the industrial Internet of Things devices, their use led to an increased attack surface that influences vulnerable physical processes. This close connection to the physical world necessitates the use of traditional safety methodologies. We propose a model-driven IT and OT impact analysis method that supports identifying vulnerabilities, most critical attack strategies, and most dangerous threat actors by analyzing attack scenarios on an abstract functional model of the system. Our impact analysis tool is developed as part of a project called Protect Me, where we are cooperating with other partners. The project aims to help medium enterprises with exploring and analyzing vulnerabilities in their operational technology infrastructure. One of our partners is ResilTech. They are developing the ResilBroccoli tool. With this tool, the user can build the conceptual model of a generic interconnected system, and they can extend the model with a list of known threats of the components from open vulnerability databases. Another partner is engineering, which is developing the rating tool, which is a risk assessment tool that supports organizations to identify major cybersecurity risks for their businesses and to support decisions related to cybersecurity investments on mitigation solutions. And Safria works on the OT risk assessment methodology and on the vulnerability and likelihood estimation approach. And our impact analysis tool helps analyze different attack scenarios and their impact on the dependability-related aspect of cyber physical systems. We are using qualitative models for this task because it's close to engineering thinking and it expresses the impacts of the different attack scenarios well. We are using the discrete operational ranges of the components. For example, for modeling a workload of a system, we can use small, medium, or high values to describe its characteristics, and qualitative models highly reduces the domain of the data because instead of having continuous domain, we can use the abstract domain with few discrete values. And on the qualitative model, we can use formal verification and validation methods and qualitative reasoning to support the impact analysis. In our approach, the close interaction between the analyst and the domain expert helps in the interpretability of the analysis, and the qualitative model expresses a well-explainable rules. For example, we can say that if the input is small and the controller is corrupted, then there is a faulty reaction in the system. Our solution uses error propagation analysis, which was initially developed for dependability and safety analysis, and we are extended it with cybersecurity aspect to explore the safety impacts of a cyber attack on a cyber physical system. In error propagation analysis, we are following a path of an error in the system and highlighting potential risk and consequences of that particular error. I would like to show you the high-level overview of the proposed workflow. This impact analysis tool supports the detailed risk analysis by analyzing attack scenarios on an abstract functional model of the system. It describes the system functions and the interactions of the components, but this model does not cover any implementation-specific details like the type of the microcontrollers or different softwares. The dynamic description of the system describes the internal behavior and the interaction between the components. Initially, the dynamics of the system describe the case where every component operates as intended. Additionally, we can reuse the safety certification models and results in form of safety constraints. The high-level vulnerabilities I described by using the high-level cybersecurity frameworks. First, the evaluation is done by a cybersecurity expert who creates an initial report, and the high-level vulnerabilities can be mapped to the components in the functional system model. Based on the high-level vulnerabilities, the faulty mutations of the component behaviors can be modeled and added to the dynamic description of the system. These mutations describe the behavior of the components in case of a successful attack. The impact analysis requires the joint handling of the functional architecture, the dynamic behavior, and the faulty mutations of the components. And the result of the impact analysis were carried out by using this error propagation analysis, and the outcome of the error propagation analysis covers the consequences of the attack scenarios where the safety constraints were violated. At the end, the analyst can further evaluate these results. This table shows the diagnostic problems that we aim to solve with the tool. In the table, the asterisk symbol represents the known parameters and the question mark symbols are the target parameters. For example, given the input, for example, the functional model of the system, and the attack scenarios, we can do impact analysis to find out the consequences of attacks, or assuming that we have the syndromes, then we can reason about the initial attack. And adding countermeasures to the equation, the mitigation of the scenarios can be calculated by mitigation analysis or mitigated impact analysis. For other analysis scenarios, we can add cost metrics like attack cost for calculating the most efficient attack, or metrics about input probability for the most probable root cause analysis.
One of the first steps of the workflow is to explore and define the attack scenarios. For this, threat modeling has to be performed. There are many cybersecurity frameworks available that define dictionaries of potential attack types on different abstraction levels. One of the specialized versions of this framework is called Attack for ICS, specialized to the needs of industrial control system on high abstraction level. It is a knowledge base that, based on real-world observations, the essence of the framework is a so-called attack matrix that lists tactics and corresponding techniques. It is a great starting point to introduce the high-level cybersecurity vulnerabilities into our impact analysis workflow. It is a much wider table, but in our simple case study, we will focus on the inhibit response function and impair process control tactics that are related to controlling the physical processes. As I mentioned, the initial goal is not to cover any hardware or software-specific attacks. However, there are databases that include technology-dependent attack patterns and weaknesses like the WITRE common attack pattern enumeration and classification or the common weakness enumeration.
Using the previously defined threat model, we can create different behavioral mutations of the components. The different mutations of the components are based on the explored attack scenarios. These mutations describe the compromised component behaviors, their fault modes, and the analysis tool selects the different component combinations which can contain both mutated and original components and runs the analysis on these selected combinations. This way, the analysis tool can select multiple compromised components, like in a real attack scenario where the attacker targets many components. We are using answer set programming as the impact analysis core engine. In general, ASP is a Prolog-like knowledge representation, knowledge fusion, and logic reasoning framework with optimization mechanisms. It can solve constraint satisfaction-like problems and results in one feasible solution that can correspond to a particular safety hazard, or we can get all the solutions with all the possible hazards. The optimization mechanisms provide the optimized solution, for example, the most dangerous hazard, and ASP supports the solution of combinatorial problems with hard and weak constraints. Hard constraints correspond to architecture of the system, or it can include other external environmental constraints about the system. While these hard constraints work as integrity constraints, weak constraints allow the definition of weights for the different error modes or mitigations for the optimization task. The extension of ASP allows the definition of temporal logic problems that handle linear temporal logic formulas. With this extension, we can handle the operational and the attack sequences, and we can generate the error propagation traces. Furthermore, ASP allows the external function calls, where we can calculate the cybersecurity related metrics. With the verification and validation power of ASP, model checking capabilities can be used. With the solution space generation, we can get the violated scenarios and we can get the proof of protection by checking the results against the criteria. And ASP is a compositional engine that allows the hierarchical modeling and analysis. We can break down big complex tasks and focus on the vulnerable parts of the system. The case study is presented on a water tank system. The system consists of a main water tank component with input and output valve actuators and then controllers. The water tank includes a water level sensor that measures the water level in the tank, and the water tank controller sends control message to the valve controllers based on the measure of the water level sensor. The system also contains a human-machine interface where the operator can see the status of the system and can react to dangerous events. The system's qualitative model includes the component's operational domains. For example, for the water level sensor, it corresponds to overloaded, full, normal, and empty, and we can add qualitative causal relations between the components. For example, the value correspondence between the water level sensor and the HMI says that if the value of the components is overloaded, then the HMI should be in the alert qualitative state. The constraints for the systems are: first, the water tank should not be overflow. The second, alert should be sent to the operator in case of a water tank overflow. In case of a cyber attack, the attacker can create multiple threats in the system. We consider that attacks can be carried out simultaneously, block command message on output valve and input valve actuators, and spoof reporting message, the controller to HMI communication channel. The attack types use the terminology from Attack for ICS framework, and based on this, and the dynamic model can be extended with the mutations of the corresponding components.
The impact analysis engine checked the violation of the safety constraints for the different attack scenarios. The attacks can be run simultaneously, or they can be activated in a specific discrete time ranges during the evaluation. This table shows the results, and as the first three columns of the table show the combination of the attack scenarios, labeled with asterisk symbol, the constraints column shows whether the safety constraint is violated or not. The combination of the three attack scenarios evaluates both safety constraints. The last column shows the proportionate cost of the different attack scenarios. And as we can see here, the most efficient attack is when the attacker only blocks the command message to the output valve and spoof the alert message.
We are developing a visual analysis environment for evaluating the results in form of a Jupyter notebook. This can be used for the analysis of extracted traces, checking the different scenarios or the vulnerabilities of the components. The Jupyter notebook enables the full exploratory data analysis by using analysis packages and different visualizations. Here we can see the extracted traces, and we can change between them, and this other example shows the different scenarios for the components. As we can see here, in this case, the block command message was active on the input and output valves. So for summary, our impact analysis tool highlights critical control paths and reasons for the consequences of security incidents. The qualitative aspect of the method decreases the state space as it does not include the full continuous model. It helps get a high-level overview of the system's critical operational modes and use the full power of formal methods, for example, to validate the countermeasures against safety constraint violations. And we can cover all dangerous cases. Thank you for your attention, and I'm open for live questions.
Thanks to the speaker for this very nice video. So as usual, we are happy to take questions. So don't be shy, please.
Yeah, hi. I have a question. about how does this threat modeling exactly work, because yeah, I saw that threat matrix, what is based on a database, but how do you process the exact threats into this matrix or from that matrix?
I believe the mic is not working.
Yeah, we can.
Oh,
I mean, at
I'm
least I'm
sorry.
not hearing.
Okay.
Okay.
It's working now? Okay.
Yeah.
Yes, now yes.
Okay, so it's based on an early cybersecurity expert report, and we can use that report to model the threats in the system. So we can see that that's a textual representation, and we use that for modeling the different mutated components.
Yeah, okay, thanks.
Okay, thanks for the question and also for the answer. Other questions? Okay, in that case, I'm asking one. No, please, Leonardo.
Very quick question. I see that you are using answer set programming. I don't know this technique very much, but I would like to ask how does it deal with state explosion problems? So if it is affected by these kind of problems, because it seems that you need to consider all the states. So.
Yes. First, it's a declarative language, and for the models, so we are using it with different industrial projects, and for those there is no problem with the design space explosion, but I think that the complexity can be a problem for bigger models. Yes, but we can use constraints to have a smaller state space.
Okay, thank you. Interesting too. I will check it out. Looks interesting.
Okay, at this point, I have another very fast question. In your talk, you mostly mentioned impact assessment, but as far as I remember, when we talk about risks, this is a combination of likelihood and impact severity in general. So in your presentation with impact, you also include something related to how likely is a threat to verify in a system, or is this something outside that you need to combine at a later stage?
Yes, we can use those aspects too to reason about the different likelihood of the attack scenarios. So we can use that aspect too in our model.
Okay. Thanks a lot. So again, we are thanking the speaker also for the answers to the questions. Now we are moving to the fourth and last presentation of this workshop. Presenter is Simon Yosnagi, and the title of the paper is Demonstrator for Dependable Edge-Based Cyber-Physical Systems. So the speaker is a master student at Budapest University of Technology and Economics, and he is an active participant of various industrial projects in the field of Internet of Things, industrial Internet of Things, and safety-critical automotive systems. Moreover, the speaker is the developer of the Gamma open source framework, in which he has responsibilities related to stochastic modeling and algorithms to analyze the behavior of the framework. So the speaker is here, so please prepare questions after the presentation, and I think that we can play the video recording. Okay, so maybe there are some technical problems.
Yes, I think the other
we are
Leonardo is not.
running. We are not running really late, so even if we are waiting some seconds more to set up the video correctly, I believe it's almost okay. Okay, so in the meanwhile,
I think José, acho que é você que está fazendo suporte aqui. José Luiz. Acho que o outro Leonardo voltou agora, deve ter tido I think there was a problem with the support, the person doing the support. Leonardo, José, are you there?
I see they are connected. Before I was not seeing Leonardo. So now I'm seeing Leonardo, but probably there are still problems. I don't know. Okay.
Hello, I'm sorry guys,
Hello.
I lost connection here.
Yeah,
Just a
we
moment.
see no problem. Okay, so yes, you need to play the last one. Yeah.
Good.
Welcome everyone, I'm Simon Nagy, and let me introduce my work in the field of cyber-physical systems. The dependable cyber-physical systems has to meet several strict extra-functional requirements. These requirements specify the system's reliability, availability, and performance. To meet these requirements, engineers use model-driven engineering, heterogeneous computing, and edge computing paradigms for the development of the system. Therefore, complex cyber-physical systems include redundant hardware and software components, load balancing algorithms, and advanced safety mechanisms. Moreover, in advanced cyber-physical systems, several emerging technologies has been applied, such as edge tensor process units and embedded GPUs, which increase the system's performance, and Docker containerization with Kubernetes deployment are also applied to increase the system's availability and reliability. We developed a demonstrator for dependable edge-based cyber-physical systems. To demonstrate and compare new technologies, development and analysis methods. We used model-driven engineering, heterogeneous computing, and edge computing paradigms for the development of the system, and we used several emerging technologies to increase the availability and the performance of the system. We also developed analysis models for extra-functional verification. For this purpose, we used the gamma composition framework, which provides a handful and high-level modeling language. We also developed a hardware-in-the-loop test environment for parametric load generation and to analyze different environmental scenarios. Moreover, with the hardware-in-the-loop test environment, we can inject different hardware and software failures into the system. Our demonstrator uses as an industrial case study, namely an intelligent traffic monitoring system provided by CAMEA and the Czech Technical University. Our system has to monitor the traffic continuously, and with computer vision and cameras, we have to detect and recognize the license plate numbers on the bypassing vehicles. Finally, we have to store all the data into a central database which was placed in the cloud. For the development of the demonstrator, we used model-driven development. So, in the first step, we developed the high-level system models. We used Magic Draw and SysML modeling language. We developed both the architecture and the behavior models in this phase. Thereafter, we developed the analysis models, we implemented the high-level engineering models, and we developed the test environment. First of all, in the modeling phase, we decomposed the license plate observation functionalities into 4 sub-functionalities, namely, we have to monitor the traffic, we have to send the images, and we have to detect the license plates in the images, and we have to recognize the license plate numbers in the images. Finally, we have to save the license plate numbers into the central database. Moreover, the license plate observation functionality has to be reliable, and we have to tolerate transient network failures, and the license plate observation functionality has to be provided fail operationally, even if a hardware of a software component becomes unavailable. In this UML structure diagram, we can see the software architecture of the demonstrator system. We developed a camera service to handle the cameras and send the images with the load balancing algorithm to the license plate detection services. In the detection services, we use a neural network to detect if there is a license plate number in the image, and we send the position of the license plates to the recognition service, which use optical character recognition to recognize the license plate numbers. Finally, we store the license plate numbers together with some telemetry data and logs into the central database. We implemented the software with the use of several emerging technologies. We used OpenCV to handle the cameras, we used TensorFlow for license plate detection, and we used PyTorch and EasyOCR for character recognition. We used PAHO MQTT for communication, and we used Influx database for data storage. All the services in the system are separated and containerized with Docker, and all the services in the system are deployed with Kubernetes. The hardware resources in the system are managed with Smarter Device Manager. We also developed a hardware-in-the-loop test environment for verification. First of all, we created a virtual traffic environment to generate a load for the system. Since the real-world deployment of cameras can be cumbersome in the early phases of the development, we used Sumo Simulator to simulate the traffic dynamics and the vehicle motion. We used the Carla simulator to render virtual camera images. Therefore, we can deploy in the simulated world virtual cameras, and we can send the virtual camera images into the camera services. We also developed a failure injector tool using Pumba in order to inject network, hardware, and software faults. So with the failure injection tool, we can test and verify the fail operational behavior of the system. With the Pumba, we can inject increased network latency. We can cause sudden availability of the services. The following structure diagram shows the hardware architecture of the demonstrator system. We used Raspberry Pis for camera devices, and we used high-performance Jetson TX2 for edge devices. The camera devices collects the data from the cameras, and the edge devices with high-performance image processing units process all the collected data. To accelerate the image processing, we use several emerging technologies. We used Coral Edge Tensor Process Unit to increase the performance of the detection services, and we use embedded NVIDIA GPUs with Pascal architecture to increase the performance of the recognition services. We also developed an analysis model for the verification of the extra functional requirements. The functional system behavior was derived from the high-level engineering SysML system models, and for the functional behavior we used state charts and gamma composition language. In addition to the functional behavior, we used a special kind of stochastic modeling language called probabilistic program to model the extra functional behavior of the hardware components. So we used a Pyro probabilistic programming language to model the processing and networking delays and the random hardware faults in the system. To summarize our work, we developed a dependable edge-based demonstrator to demonstrate and compare new technologies and analysis and development methods. We used model-driven engineering, edge computing, and heterogeneous computing paradigms for the development of the system. We used several emerging technologies such as Docker containerization, Kubernetes deployment, and TensorFlow artificial intelligence. We also developed analysis models for verification, and we developed a hardware-in-the-loop test environment for parametric load generation and for fault injection. Thank you for your attention.
Thank you for the presentation. So as usual, time for questions. So I can start this time, I believe. So I would like to ask the following question. I saw that you have some neural network which is taking place in image recognition, okay, mostly image processing. So question is, are you training your network from scratch, or are you using some available network to transfer learning to adapt the already available network to your domain?
Excuse me, I had a network issue. Could you repeat the question?
Oh, sorry, yes. Question was about the neural network you use for image processing. Question is, do you train your neural network from scratch, or do you use an existing network, ResNet, MobileNet, AlexNet, whatever, and then you transfer learn from these existing networks?
We use transfer learning to generate this specific neural network. We used a generic neural network provided by Google, which could recognize cars, and we used transfer learning to make the neural network recognize license plate instead of cars. So we retrained the upper layers of the Google's neural network.
Okay, clear. Thanks for the answer. Other questions?
Yes, I have one also, but maybe there is also someone.
Yeah. Hi. My question is, do you try any actual hardware feed to test your solution? I mean, real camera applied in some real highway or anywhere, or is this hardware in loop test only for the simulator?
We used our first solution was a small model car and a real camera, but we didn't use real world recordings yet for testing.
But based on your answer, I assume that you plan to test this out in real world.
Yes, but the first priority of our system is to provide a case study for further research, because, as it was mentioned in my introduction, I currently develop the Gamma modeling and analysis framework, and I realized that most of the industrial case studies in field of Industry 4.0 industrial IoT, the case studies are closed, not available, and I wanted to develop a case study which is publicly available and which can be used for development by anyone.
Nice, very nice. Thank you for your answer.
Okay, thanks again for the answer. Other questions?
Yeah, I had one, but I think he has already answered actually. So my question was if this demonstrator was going to be released as open source or public demonstrator, because I think it's very interesting that you joined a lot of tools, and probably it's not an easy thing. So it would be exactly nice if you can share, and with maybe procedures to build all these demonstrators. Yeah.
I have to mention that we put a link to the GitHub repository of our demonstrator, but this link is not available yet. But there is a temporal repository which is currently available, and all the source code which are developed are open and can be used. All the shell scripts, all the Python programs, even the neural networks.
Okay.
And I have to mention that all the used hardware parts are publicly available, so we haven't used any custom hardware.
Okay, nice. Very, very, very nice. Thank you. So the link is in the paper, I believe. You mentioned the link is in the paper is not working yet, but you are probably building this repository and
yes, but in a few days I think it will be available, because just we have to find the correct person's license for the project.
Sure, yeah, it's understandable too. Yeah, sure. Okay, thank you. Yeah, very interesting.
Okay, any other question? Let's see.
Yeah, if you have also some questions on previous presentations, we have like 5 minutes.
They want you to have 5 minutes of conclusions, Leonardo. That's why they are not asking. Okay, if there is nobody else who has questions, thanks everybody for the participation to this session. I mean, I'm leaving the microphone to Leonardo. Last thing I want to mention is I'm begging the pardon of all the presenters. I tried my best to pronounce the names correctly, but clearly it didn't work. Okay, so sorry for the wrong accent and pronunciations. I hope you can get over this, okay? And thanks for joining this session.
Okay, thank you, Tommaso, for chairing this session, and thank you for all the interesting presentations and discussions that we had, for the questions, and for everyone attending. I see that we have a good number of people attending, so I think it's going well. So I think now we can close this session. Then we will resume in after 1 hour and a half, basically. Now we have a break now, 30 minutes, and then there will be the keynote for the main event, from a LADC SBESC keynote, and then we resume at 4:30 Brazilian time, which is GMT -3. Okay, so thank you everybody, and I think we can close this session now. Thank you, and see you later.